the so-called neural network potentials. And just to show you, I just did it half an hour ago, checked the references to this term embedded atom method, which is 800,000. And then I did the same for this neural network potentials. You get 2.5 million hits. Yeah? So apparently it's very fancy at the moment. Yeah? So anything which has this term, artificial intelligence, neural network, and so on. But it is a powerful method, I would say. One has to be aware also of restrictions, but we'll see. Here I give some key references. It started already 15 years ago, 2007, but I think the real applications came up here in the early 2020s or so. And in particular here you find real usable potentials for aluminum copper, the system we are interested in. But you also find tools to generate your own potentials. And therefore, of course, it's probably important to understand what they are doing and how they are constructed. That's what I'm going to explain here. Neural network potentials. And people just speak of NNP. Basically, I think it's a doubling. They speak of NNP potentials, which is twice the same. But anyhow, so what the basic idea is, instead what we did before, to fit such a potential, we use, I don't know, 5, 10 or so experimental data points or DFT data points. Yeah? And this can be fitted to so many parameters, 10 parameters or so. This, of course, gives you a reasonable approximation if you did it well, a poor approximation if it does not converge or so. Yeah? Here, as usual in this artificial intelligence business, the approach is the other way around. You use a huge number of, or huge amount of input data. You use a huge amount of fitting parameters, and how to bring them together, there you need this automated procedure called artificial intelligence or neural network methods. Yeah. So the idea is not too difficult to understand. The first step is you generate many atomic configurations. I think in this case of the aluminum copper system, for the binary system, they used like 1,000 or so. For a ternary or quaternary case, they used, I think, 5,000 or so. This can be not only different structures. Of course, it's important to use different intermetallic structures. But also defect data. And whatever you find, you generate these structures. Then you calculate their energy using ab initio methods, typically. Yeah? And what is very important, you also do a structural relaxation. In most DFT codes, you can adjust, for example, the lattice parameter. Yeah? There's if you are not in the optimum configuration, say you chose a too large lattice constant at the beginning, you can calculate the forces similar to what you do in MD, and then relax the structure until you reach a point of zero forces of minimum energy. And then in the next step, you split this total energy. If you have just a homogeneous aluminum copper alloy, you basically have one or two, but this also can depend on the surrounding. So you split your energy, the configuration, but these single atoms, they differ in their surrounding. Yeah? So they are not all, it's not just the energy of one aluminum atom and of a copper atom, but of an aluminum atom surrounded by this and that. So this is done in the next step. You describe the local environment. In simple functions. Or simple. And these symmetry functions, that's, I think, where the most efforts is in. So they are called symmetry functions because they are invariant under certain transformations. For example, you can describe part of this configuration by a spherical part, so something which is rotational invariant. So that's a typical pair function would correspond to a typical pair function. You have an aluminum here, a copper here, and something spherical. So it's depending only on the distance of these two. But also non-spherical. And one choice could be that you just approximate it by a number of Gaussians. So what are these parameters? This function fc is just a cutoff function, as we saw before. You want the range of these functions only be limited. And this is the distance Rij. Rij is the distance to the neighboring atoms, over which we forms a summation. And the eta is the fitting parameter, so that's the range of the half width of this Gaussian. So basically, this is a fitting parameter.
Mm-hmm. Including like how do you make that if you want a copper aluminum
Hmm?
Shall we create the structure like FCC or BCC and then making to relaxation, or directly only 2 atoms?
No. I will show the example how they actually did it. They used like, I think, 990 different structures, all kinds of intermetallics. So I think there's aluminum 2 copper phase, aluminum copper 2 and 3, all these phases. And then you can put defects into these phases or antisites or different things. Yeah? And for all these, you calculate the energy. So you know, for example, if you have an aluminum 2 copper.
Energy means single point energy.
No, the total energy of this the box containing this unit cell. Yeah.
And this structural relaxation is geometry optimization?
Yeah.
Okay.
Just, I mean, for FCC it's a bit boring. It's mostly only the lattice parameter. But for a tetragonal phase, it can be the A/C ratio and all these things. Yeah. Or if you have more complicated intermetallics, perhaps the relaxation of the atoms, all these things. And in particular, of course, if you are studying defects, if you put a vacancy, how much do the atoms relax around the vacancy? All this I mean by structural relaxation, energy minimization. Of this type here. So they have a strange normalization factor. And an angle, of course, requires at least 3 atoms. Times again such a Gaussian. K squared plus R JK squared, and again times cutoff functions. Yeah. So now you have so many experimental or DFT data, structures and so on. You have so many functions, all with certain number of fitting parameters. And this you feed into a neural network and try to optimize the set of parameters or fitting parameters. And then you check backwards whether this fits to your input results. And I will only briefly show one paper where they did this for aluminum copper. It's a kind of copyright problem here that I don't show, or that I did not copy these things into my slides. Here you see these functions here. And not only they did not only do one neural network run, but many, and always got different potentials. The one I will show in application, or I will show 2 of them, NNP 10 and NNP 11. And here you see the quality of their results. So here, I don't know whether you can read it, are all the structures they use. So there's aluminum 5, copper 5, aluminum 2 copper, and so on. So a huge number of different structures. And here you see the atomic volume. Here you see the energy of the structure. Here's the atomic volume. Here some elastic constants, and so on. And they did it here, here for DFT. That's a black line. ADP is another type of phenomenological potential. And then here is the NNP 11. And you see how close, so my mouse is lost. So that's the important one, the blue, how closely it fits to this black line. And this error bars here, these are for other fits. Yeah? They did it, as I said, not only once, but with different approaches, different starting parameters or so for this neural network. And they all come pretty close together. Same here for the atomic volume. So they are very close. And here you see cases here, for example, for the elastic constants, where the phenomenological potential more or less completely fails, while this NMP potential still gives reasonable results. Here you see this is for the different structures. Yeah? I don't know which structure is so difficult. The C44, what was it here for aluminum copper 3 or so. Yeah? One of the structures seemed to be a bit strange, difficult to explain, but for most of the structures it gives pretty convincing results. Yeah? And here are other parameters what they got out of their simulations. I will just show a brief application we did ourselves. We used this NNP 10 and NNP 11 for topics we are interested in. And this is the formation of Gini-Preston zones in aluminum copper. I am not sure whether all of you are familiar with this. In aluminum copper you have this first natural aging or natural hardening reaction where the copper atoms form microscopic clusters, monoatomic thickness or one atom thickness on 100 planes. And of course one can explain it with elastic strain. The copper atoms are a bit smaller than the aluminum atoms. But there might be also some kinetic restrictions, so that if copper atoms diffuse through the aluminum lattice, that they prefer to migrate to the edges of this monoatomic plate, instead of approaching the plane. And that's what we tried here. And that's a comparison, basically these two here. That's something else. I come to it in a moment. That's a side view and the top view of aluminum crystal containing here such a copper plate. So it's a spherical plate, but here in the cross section it has 5 atoms diameter. And that's not unrealistic. I mean, these Gini-Preston zones, perhaps there are 10 or 20 atoms in diameter. They are pretty small. Yeah? And what is shown here is the energy for a copper atom sitting on any of these sides around it. Yeah? So we calculate, or the postdoc of mine who did this calculations, he calculated the energy of a copper atom here. Here you see the scale, so here it's just the average, does not matter. Here you see sites which have much higher energy. Yeah? And here you find sites which have lower energy. This was done here, this column, using Monte Carlo with a cluster expansion. I come to this later on. And here you see the comparison with this neural network potential, which includes all the relaxations and everything, which is, I would say, much more precise. And what you nicely see is here's a Gini-Preston zone, and here are places where the copper atoms have higher energy, so they don't tend to go here. The only way they can reach the Gini-Preston zone is from the side here. Here you have slightly higher probability to find the atom. Yeah? Similar here on the top view, so that's just rotated by 90 degrees. You have the Gini-Preston zone here, and the copper atoms can easily reach the plates from the side, but not from the top. So for me, this indicates that there is, besides this elastic contribution, also a strong kinetic favoring of this plate-like structure instead of thicker atoms. This was with this potential NNP10, and the same or similar result we tried with the NNP11, which was the one also I showed in these slides, which seems to be a bit better. And the nice thing, what you see here, is that there is a zone on top of the Guinea-Preston zone, which seems to be forbidden for further copper atoms. Yeah? And indeed, I don't know, again, how familiar you are with aluminum copper metallurgy. There's these Guinea-Preston zones, and there's something called GP2 zones. Yeah? These are two copper plates on top of each other with a pretty precise distance of 3 atomic layers in between. Yeah? And here you see the next copper could be here. Yeah? So this nicely fits to what is experimentally found, and we study them also in electron microscopy with modern electron microscopes. You can see all the copper atoms one by one and how close they come to precipitate and so on. You also see this strongly increased probability here to reach the copper plate. Yeah? The development of such an NNP potential, of course, requires a lot of DFT calculations. But then you have to compare it to ab initio molecular dynamics. This is also a method which I did not yet mention here. Ab initio molecular dynamics means that for every step we calculate the energy using a DFT. And from this energy you calculate the forces. Then you do your MD step. And then you start from before. Yeah? So this is a very heavy tool. And compared to this, it's much faster. So it allows to reach precision, what people claim, close to what is obtained in ab initio MD. But compared to this, much faster. Yeah? Question is how far it is. These are the points I gave in the beginning. How far is it transferable? Yeah? It fits, I don't know, hundreds or thousands of structures. So if we now put it into a structure which we did not consider before, or if we have a more complicated defect, does it still give reasonable results? So I think there are still tests remaining open. Since it's rather new, I think we have to make our experience with it. It is a promising method, but for sure it will not solve all the problems we have. Okay, and you can make your own experiments with this once you are familiar with lumps. It is implemented into lumps, or you can put it into lumps. And there is this also open source code, I think it's called N2P2 or so, to generate these potentials. So whenever you like, you can also try to generate your own potential. Okay. You can look into these references. I think in particular these by Marchand and Curtin and Marchand and Jane. I think these are the ones which are very clear and where you can follow the steps, how they obtain the potentials. And I think, I'm not sure, my student, I think he asked them for the potential parameters. But I think in one of the papers at least, they also give, perhaps I should show it again. I think they also give the list of the parameters. This one is for a quaternary system, so aluminum, copper, magnesium, zinc. And somewhere here they give this long list of parameters. So if if they don't make it available, you can sit down and copy them from the publication. I thought it was, yeah. I don't know. I mean, they use part of this, I think, as a training data. I think they yeah, but not all. I think they use. I mean, at some point you have to check whether your fitted data predicts.
He is asking which is the data set from which they took the.
Oh yeah, this is just the DFT data. Yeah, yeah.
Okay, sir.
Some thousand or something.
Yeah, I think they give it here in this. But what I was going to show is this long list of parameters. And this is, of course, I mean, that's the whole story behind it. You have so many parameters, not only 10 like in EAM here. So it starts here. This is for the radial symmetry functions. So for aluminum, aluminum, copper, aluminum, aluminum, magnesium, and somewhere below is aluminum, zinc, copper, copper, magnesium, aluminum. All these functions, you get these parameters. These are only the spherical symmetric. Here these are the angular functions. And what is the third? So what I wanted to say is these parameters somehow are published. Of course, it would be a bit boring to just copy them from this long list. But I think they make it also available for applications. And for this other simple aluminum copper system, my student had to ask him, I think, to send him the parameters. Here, but they don't explain precisely what type of neural network they applied here. But yeah, this paper is available. I think it was ACTA or FISREF or so.
It's not essential now. We will start a little bit later. I'll start with the presentation, then we'll go back to the scripts. But from today on, I think it would be much more useful if you start doing along with me, and if there are any issues. I don't still use LAMPS regularly, but there are people here who use it much more regularly, so who will be able to help you with. One of the purposes of this workshop for me at least is that first time when you start, there is a huge amount of time that the student has to spend, and in our group Sushil has done for LAMPS and Nagarajan has done for Sparks. So at least after that, the others when they use it should be much more quicker. And we have found that the easiest way is that you take an existing script, run it, see what it does, and try to understand and try to do your modifications, right. So at least that much of threshold you should cross in this course in these 10 days. So that is the aim, because of which please do have the computers, try to run. So this is the first session. There is an extra M which should not be there. This is the outline of what we want to do. One slide about LAMPS, and then I want to solve 3 problems. And the first problem, the lattice parameter evaluation, is one where I have gone through the script line by line. I have explained what each line does. And once you have an idea, then the other scripts are more complicated, but probably easier to follow, because now you know what each block means or what it is doing and so on. Having said that, you would learn LAMPS a lot more easier if you get into the habit of reading the manuals. The manual is some 2600 pages or so. Okay. So obviously I do not expect you to start reading from beginning till end. But what you should do is that when you see example scripts like this, just go to that particular command and read those 2 pages. As you will realize, and as Sushil will tell you, first time reading or second time reading or even third time reading, you do not understand everything that is there in the manual. Okay. So maybe some parts you do not understand, that is okay, you still read and later or keep thinking about, maybe at some point later you will understand the much finer points or nuances. Okay. So it takes time, and that is how you develop the expertise in any case, but you should have the habit of reading the manual, right. Yesterday or day before yesterday, somebody was asking, I want YouTube videos, right. It is true that you can learn a little bit through that methodology, but that is not a better solution if you want to go in depth. Okay. There is a point where you should graduate from watching videos and doing stuff to reading and understanding and doing. Okay. The second thing, which again most of the times people do not do, and especially at the beginning you tend to make mistake, is not reading the log files that LAMPS generates. Okay. recently we had a meeting with one of our collaborators. The student is learning lamps and some of the results did not make sense, and then we went and found out that he tried to do a minimization. The minimization did not converge, and that is written explicitly there in the log file. If you see, there are still large forces on the atoms and the energy is not minimum and there is huge difference and so on. But of course, the program runs and it comes out, there is some numbers dumped. So, you can take them and plot them, but unless you pay attention and every point you ask, is this the right result? I mean, have I reached the last point, or is it reliable, or is there something else I need to do? If you do not do that, then again you do not benefit from that. I mean, as you will see, these things are easy. I have had several undergraduates pick up how to run a LAMP script by taking an example code, modifying it. You can do it in a week or so, but you will not develop any expertise, or you will not be able to solve important problems unless you get into the habit of trying to understand everything, with the full knowledge that you will not understand everything at the beginning. It takes longer time, and even now there are points which I do not understand, but I think that is part of the game, that is okay for us. At least your understanding should deepen as time goes by. So, let us start with lamps. What is lamps? Lamps is a large scale atomic and molecular massively parallel simulator. Okay. If you have access to larger clusters or high performance computing machines, you can run larger simulations. Okay. And some of these simulations make it to the cover pages of journals like Nature and Science, because they have been run really large scale systems. Okay. I do not think we have access to such systems yet in the country, but in any case, I mean, if you want to do some research or want to publish something, you should be able to run on a large size system that would necessarily require that you use one of the high performance computing machines. You can run on your laptop, you can understand things, but at some point you may have to graduate to, and that is why it is also important that if you want to use things like LAMP Sparks, learn a little bit of Linux, because many of these machines will also have the operating system as some flavor of Linux. I think CentOS is more common in many of the machines that we use, but it could be any one of those. And I also like lamps for another reason. It does classical MD, of course Ferdy mentioned ab initio MD, so this does classical MD, and the emphasis is specifically on materials modeling. If you go to the lamps website, they have other MD programs and they tell what they are for. There are things like GROMACS which they say are more recent, and there are others NAMD and some others that they mention, which is meant for biological systems or polymeric systems and so on. So, but for materials modeling, lamps has been used for quite some time now, and is quite good in our experience. So, this is an open source code that is developed by Sandia National Laboratories. Go to this site lamps.org. It has codes and executables for download, lots of examples, and this documentation running into 2600 pages. There is a manual, and there are several forums where you can interact with other people, and one of the authors at least responds to messages, and in this fora somebody posts a question or something, he will still come take the time to answer. Of course, should not go post some simple minded things, you will lose your reputation in these forums, but you read through, you understand, and then you ask a more technical question, one of them will step in and give you the answer also, to which extent this is a really nice thing. And whatever you are going to see is Ubuntu 22.04 is my operating system, and this is a LAMPS stable version which got released on 23rd June 2022. That is the version that I loaded. Like I was mentioning this afternoon, yesterday I had to load, delete, go through this cycle few times. I think now it is okay, which is working, we will see. Yeah. 2020, it should be okay, it should work. I also had, I removed it and put the latest one just to. Yeah.
Problem with the 2022 version, I don't know why.
I see.
think they bring out a new version every week or so.
This is a stable one. So.
I have one from 3rd of August or so.
No, I didn't try to. Yeah, load the stable one.
No, sir, I loaded the stable one only.
You still had difficulty.
No, so like when I loaded the stable one, it was not untarring only.
Okay.
So then I loaded the 2021 and got untarred and I.
Okay, fine, it should work. But just I am telling because I mean somebody wants to know what version, etc. So this is the information. Okay, so I am going to discuss a script for finding out the lattice parameter, and this script comes from Sushil. Okay, so he is here, so I do not have to worry too much about answering questions. And this is based on a paper that we recently published in Computational Material Science. And as you will see, Sushil also has documented. So, you initialize the simulation, set up the lattice and populate it, define the potential, define the simulation parameters, run and get the output. That is all. It is a very, very simple script. What we are going to do is to start with a lattice which is slightly away from the equilibrium lattice parameter, and it is going to run and it is going to get to the equilibrium lattice parameter and it is going to come out. That is all we are trying to do. There is one more aspect which is related to after the output visualization. Today I am going to show you a couple of shortcuts which are not great, but will still serve the purpose for us today. But we will have a separate session just on visualization, because that is also very important. You can run lots of simulations, you can have lots of interesting results, but unless you try to visualize, like reading the log files, you should also visualize in many different ways, and that is where you actually develop an understanding for what is happening. Okay. So, we will have a session for visualization separately, but for today I am going to take a shortcut. I am going to use some pre-built commands of LAMPS and do the, and this is also sort of advertisement for my next GIAN course. So, there is also some phase field crystal modeling, and that is the author, one of the authors who is coming as the instructor for the other course. Okay. So, okay. So, I am going to open the script and show, but let us go through the commands. This is a command and that is the comment. So, clear is the first command. What does it do? It clears memory, removes all variables that are stored and resets everything to default values if you have changed and so on. Okay. Okay. By the way, this slide is also available, so you do not have to. The units we are going to use is called metal. Okay. So, this is self-explanatory. This is a set of units that we are going to use in this simulation, and the units have different names. There is an LJ, there is metals, there is SI, there is CGS. Okay. So, there are many, and it becomes important to know what values are used. Suppose if I say units metal, what is the time scale? That you need to know, because then you will get a time step. Should I give 1 as time step or 0.1, 0.01, 0.001? For that you need to know actually what it is, and this is where the manual helps. If you go to the manual, I found that this PDF file is much slower than online I can search. This is much slower. So, the online version I prefer, which is much better. Okay. So, here you can see. Okay, so, you can see metal, the mass is in grams per mole, distances are in angstroms, time is in picoseconds, right. And yesterday we had this discussion, for integration what should be the time scale? Femto. So, you should use some time scale as 0.001 for the integration, because this is the time scale that is being used in the metal unit. Okay. So, it is important to do that. Yeah, so this is the LAMPS page, and download and manual. This page is really nice, and you can search and it is quite quick. So, it is the same page, units can be metal, units can be LJ and so on, and so real units also you can use. Okay. Metal you can use, I do not know what they mean by real, but you can look at the values and you will know. So, SI you can use, CGS you can use. There is an electron style also, distances are in Bohr and mass is in atomic mass units and so on. Okay. There is a micro.
Somewhere say energies in kilocalorie
Yeah. That was, I think, in real or something.
These guys know what it is.
And there is a nano style where mass is in attograms. I don't know how much it is.
18.
Huh?
10 to minus
18,
18.
is it? So that's for what? For an electron or something?
No, I mean, an atom has 10 to minus 25 or so kilogram.
Ah, okay.
Okay, yeah, attogram is 10 to minus 18 gram.
Oh, that's a 10 power minus 21.
Kilogram.
I see. So they also give this very usefully, right? For style metal, dt is 0.001 picoseconds and skin is 2 angstroms and so on. Okay. So please do use this page as often as you can. Okay. So that is what units metal means, right? So we said units metal, and it is a 3D simulation, that is again self explanatory, you do not have to worry. The boundary condition is PPP, which is periodic in all 3 dimensions, x, y, z. There are several other ones. Shrink wrap is another common boundary condition, where you will have a surface, it will not periodically repeat, but it will also not allow atoms to escape from the box. Shrink wrap as in, you know, the plastic cover that you put and wrap your boxes. So, it is shrink wrap, nothing can leave. So, that is common, and other types of boundary conditions, if you want to look at, please go take a look at the manual and look for boundary, you will see what are all the types that are available for you. Atom style is atomic, okay. This is a metal, specifically Sushil has written it for iron BCC structure. So, each lattice point is occupied by one atom. So, and this one is something related to, this is not something that we discussed in the course as yet, okay. Because I am looking at pair potentials, and because I need to know within the cutoff distance which are all the other atoms which are sitting, for which I have to calculate the pairwise interaction, typically one generates what is known as a neighbor list, and that neighbor list is updated once in a while. And the way you do is that I take an atom and I look at some distance, I do not keep it exactly the cutoff distance, but I give some margin, so that some atom goes slightly here and there will not affect, I will still be able to do. Once in a while, especially if any of the atoms have gone half the distance of this skin distance that I have, that skin distance it is at 2 angstroms. So, some atom moves more than 1 angstrom on that skin, then I will regenerate the neighbor list. Now, LAMMPS is a parallel code, and so there are several processors which are doing it. What you are doing here is to tell LAMMPS how you want this data to be handled. When you say map array, it gives this copy of lookup table to every processor. Okay. Now, if memory is a problem, you are supposed to pass hash, map hash or something. Okay. This information is there in the manual. This is something related to the programming and the way the algorithm is implemented. We implemented a very simple minded MD yesterday, which did not talk about the neighbor list and linked list and things like that, which are, if you go to a textbook like Allen and Tildesley, you will see, especially people who are, Allen and Tildesley is for liquids. If you do MD simulations for liquids, things are all moving around. So, these things become much more important, and starting from how you label the different atoms and molecules and so on, there are algorithms which talk about, which we did not talk about. But if you are using LAMMPS, because it has all these capabilities and this does all these things, you have to know some of these things, and yeah. I mean, all that is done automatically at the back end by LAMMPS code. What you are telling is whether you will give a lookup table of the atom IDs to every processor, right. If you give that, you are loading the memory of every processor.
Yes.
Sometimes you might have difficulties with loading like that with memory, in which case you have to give the hash. Okay. So, we do not, I mean, this is faster because every processor has a copy, so it does not have to worry and so on. Okay. So, this is just a key word that you pass on to the computer as to how it should handle this information. Okay. It becomes essential because you have to tell one way or another, and we have not even discussed about this aspect in the course yet, right. So I am just pointing out that there are these things, and you will see the skin distance and how the neighbor should modify, etc. There are some keywords which will also come later, which are related to the implementational aspects. So this is the initialization. Now we want to set up the lattice and populate it. So we set up a BCC lattice with 2.65 as the lattice parameter. What is the units of 2.65? Metal units. In metal units, what is the units of length? Angstroms. So this is 2.65 angstroms. Okay. So it is important for you to have these numbers in mind or look up at least in the initial stages. Then we define a region and we call that as box. Okay. And the region keyword is block. So we are going to define a block, and its x min x max, y min y max, z min z max is given in lattice units as 0 to 1, 0 to 1, 0 to 1. Okay, that is the box that you are defining, and create box is the command to create this box which you defined, and 1 tells you the type of atoms, and I am going to make pure iron crystal. So that is why there is only one type of atoms. You can, for example, copper aluminum you want to make, there will be 2 types of atoms, types 1 and 2. Okay. And that is what is going to populate this box, this region you have defined, and you have given a name to this region called box, and you create that box by populating it with one type of atoms. Because it is a BCC lattice, you also have to tell what is the orientation of the unit cell of that lattice with respect to the simulation frame of reference. X, Y, Z of the simulation frame aligned along which directions of the BCC unit cell, that is what is given here. Orient X with 1 0 0, orient Y with 0 1 0, orient Z with 0 0 1, basically they align. It need not be. We typically do simulations where Z is aligned with 1 1 1 of FCC and 1 1 bar 2 1 bar 1 0 and 1 1 bar 2, right, because that is what will dot with 0 with both 1 1 1 and 1 bar 1 0. Okay. So, 3 perpendicular directions. So, you can align x with 1 1 bar 2 and y with 1 bar 1 0 and z with 1 1 1 or z with bar 1 bar 1 bar 1, and so whichever one you want you can align. Okay. So, this is just basically orienting the lattice with respect to the simulation frame of reference. Create atoms of type 1 in the box and replicate. I have commented it out. If you do replicate, it will take the same. Suppose what did this do? I had 1 units of lattice, right. Now, if I say replicate it once, it will put that and replicate along once along x, once along y, once along z. So, which means it will make 1 unit cell, put it there, put it there, put it there, right. So, you will have 1. Now, if you say 2 replications, it will make 4 because it had replicated. So, it has instead of 1 by 1 by 1, it has 2 by 2 by 2, that is what will get replicated. So, you will get 4 by 4 by 4. Okay, you can say 2 2 2, then you will get 4 by 4 by 4. So, it will become 1, it will take and it will put along x, y, z. So, you will get 2, 2 4 and 4 8. Now, if you say second replicate, this will get replicated.
No, so sir, like what do you mean by saying second replicate?
I can say replicate 2 2 2. That does not mean that 2 unit cells it will make. Replicate is take the box and make it in 3 dimension replicate. Yeah, it will be 1 unit cell. I will show you. Yeah, yeah.
Now sir, if I give 2, 2, 2, it means 8 unit cells will come.
8 unit cells will come. Yeah, 2 to the power 3.
Okay.
Okay. Yeah.
Sir, and another thing that when you are giving like region box block,
Hmm.
then 0, 1, 0, 1, 0, 1 you are mentioning, and like you are giving the unit cell lattice. So this 0, 1, 0, 1 means that it will start from 0 and like it will end at 2.65 angstrom, the x.
In units of lattice, yeah, yeah, yeah. And that is also going to change, because remember, this is not actually the equilibrium. Yeah, it's going to change, but initial one it will make with this. Okay. Now you have to define the potential, and the potential is defined using pair style and pair coefficient. Pair style is AM, and even though it is a pure metal, we will still call it as alloy, because the AM for alloy also is the same. Okay. And you just saw that EAM is actually not just pair, right, it also has this electron cloud information. But as far as LAMPS is concerned, it is considered as pair because it has to generate the neighbor list. So, any potential for which it has to generate neighbor list, that is any potential which has a pair component is a pair potential. Okay. EM is not strictly a pair potential, but the pair style is AM alloy. And pair coefficient, I am using a wild card. If you had, for example, iron aluminum, then it will be iron will be type 1, aluminum will be type 2, you would have defined in the types. Then 1 1, what is the interaction? 2 2, what is the interaction? 1 2, what is the interaction? All three you have to give.
So like all three will be given in 3 separate lines, or
So, the EAM file might have all the information. Okay. So, you just have to say 1 1 and then it is in EAM for iron, 2 2 it is in EAM for aluminum.
so like while writing in the script, how do we write it?
We will come, you want to see for a alloy, we will come, but for now because we have only one, we use wild card. So, there is only 1 1 interaction, and for all of that, I mean you can also write wild card for if your potential file has everything, multiple components is there, you can go, and the potential will have that information. This is the aluminum information, this is the iron aluminum, etc. So, it will take. But if you are doing LJ, for example, you want to give for 1 1 this is the interaction, 2 2 this is the interaction, 1 2 this is the interaction. So, it is possible to use wild card, which means go read this file and for this element this is the information you have to take, or you can say specifically for this is the interaction and so on, and whatever is the most latest pair coefficient command that will overwrite whatever is there earlier. Okay. For example, you can have LJ, you can have a wild card LJ where you will define for all the interactions some parameters, and then you will say 4 and 5 this is the interaction, the next line, then for 4 and 5 it will be overwritten. Okay, that you have to remember. So, you might think that, oh, in the 5th line I said so, it does not matter, whatever is the latest one which you say is the one that LAMPS will consider for that particular pair. Okay. Again, this information is there in the manual, you can go look up, it will say that whatever is the latest that will override the previous commands. Here again, this is what I said, neighbor list, how far you have to go beyond the force cutoff. Force cutoff is already given, the EAM potential file will have the force cutoff. If it is LJ, you will say LJ / cut and you will say how much is the cutoff, but it will go a skin distance beyond the cutoff, that distance is what is given, and for that distance up to that it will bin, that is if you take one atom it will take the force cutoff distance, beyond that 2 angstroms whichever atom is there they will all be in the neighbor list for this atom to calculate the pair potentials, and how much time you should take before rebuilding the neighbor list, because atoms are moving, it might require rebuilding. And suppose if you are on a lattice and things are not moving much, neighbor list is costly to calculate, right. You have to look at every atom, find out how much distance they are from each other and put and so on. So, we want to avoid this as much as possible. So, if it is on a lattice and things are not moving much, you do not have to update your neighbor list at all, right. Because of which you say neighbor modify, delay 10 means before 10 steps it will certainly not do a neighbor list. Even that, if you say check yes, even this after 10 steps it will do only if any of the atoms in that skin region have moved more than half the distance of this skin that you have given. Otherwise, it will not update, it will not do the neighbor list at all. Once in 10 steps it will go look at, okay, most of them are wherever they are and they have not moved much, it will move on to the simulation. After 10 steps again it will come and check, and if has not moved much it will go. But suppose suddenly one part something has melted or some atom has moved, then it has changed, it will regenerate the neighbor list and then come back and continue with the simulation. Okay. Because this is a costlier process, that is why it takes care. You can say check no, which means once in 10 steps it will necessarily do. If you say delay 10, certainly for 10 steps it will not do, okay. But there are other ways, you can ask the algorithm to look it up for itself or do it according to its algorithm and so on. So, those commands are also there. So, neighbor modify, if you go in the manual you will get all the commands, but this is what Sushil has been using and this is what I want to show, but this is related to the neighbor list which we have not discussed at all as part of this as yet. Okay. So, we set the time step counter to 0 and our time step is 0.001. So, keep in mind that the units are metal. So, this is self explanatory what it is. And then there is this command called fix and unfix. What is this fix is doing? It is considering atoms of type 1, it is considering all of them and it is taking the box and it is relaxing. Okay. That is what this fix is doing. This fix is basically relaxing the given box. Why are we relaxing? Because we know that we have given a lattice parameter which is not the equilibrium lattice parameter for iron, and we want to relax to get to the equilibrium lattice parameter. That is what we are doing. And at any one iteration step, the volume cannot change more than 0.001. That is what the Vmax is telling. Relax and then suddenly it should not become too large. We do not want that. So, this is fix 1 that we are making. So, that is the number 1 and all atoms you are applying this fix to, and that is relaxing the box. And at any one iteration the volume cannot change more than 0.001. And what does this ISO mean? ISO means in the x, y, z the relaxations are going to be identical. This is because we are looking at a cubic system and with the principal axis of the crystallographic direction aligned with our x, y, z. If you are relaxing in some other direction, you may have to use unisoed, you have to allow for. Okay. So, ISO means all three diagonal together. So, it will calculate the pressures and it will do. The minimization style is called CG, which is the conjugate gradient minimization. I do not know if any of you have used conjugate gradient or familiar with conjugate gradient. If not, there is a nice article which I always like. It is called conjugate gradient without the agonizing pain, version 2 and 1/4 or something like that. Okay, you can look up. This is some computer scientist from Carnegie Mellon University who has explained using again Octave very nicely what the conjugate gradient algorithm is and how it works and so on. And there is a quantity, there is a line search, and this quantity D max is basically maximum distance for line search when you do the conjugate gradient. So, if you do not know the algorithm, go look it up, and basically we are saying do a conjugate gradient minimization and giving some parameters associated with how that minimization has to be carried out. The minimization, there is a tolerance on energy, there is a tolerance on force, maximum iterations and maximum number of function evaluations are potential evaluations. Okay. Those are the numbers. These should be really large, because you do want the program to come out after it achieves this. You put it some 5 or 10 and then it reaches the maximum iteration or maximum evaluation and it comes out, then it won't have minimized actually. And I think whichever is the earlier that is achieved, E tolerance or F tolerance, it will come out, but you can check the manual and you will get the information, why it came out, how it came out, etc. That is why it is important to go read the log. And associated with the fix is the unfixed, whatever we called as 1, and that is unfixed. Yeah, this is energy minimization. So, I am getting the lattice parameter at 0 Kelvin now. I did not mention temperature, but if I give temperature and if I do want to know the lattice parameter, I can't use minimize to get the lattice parameter, because it will quench, the velocities are 0, which is equivalent to 0 Kelvin. So, in that case what I have to do is I have to equilibrate the box at that temperature, then take the Lx, Ly, Lz. In all steps they will not be equal. I have to take the average of that, find out how many unit cells I had, divide by that to get an lattice parameter, but that lattice parameter will come with an error bar, because then I have to take lots of statistics. So, I will get a mean, I will also get a standard deviation or variance.
Sir, like I have a question here, that like if I am performing like suppose if I want to find out the lattice parameter, then the energy minimization that which I am doing, that should be at the prescribed temperature at which I want to do my further production run.
Right. Right. So, this lattice parameter that I am showing you is for calculating it at 0 Kelvin.
Okay, this is at 0.
Okay. But we can calculate at other temperature. You can run an NVT, you can get to 300 and you keep the system, you equilibrate, make sure that it has equilibrated. Now, you start measuring the box size. Okay. In fact, we have measured up to the melting temperature. We have calculated the lattice parameter at near about the melting temperature also. But there it is not minimization that tells you, right. You have to keep the system, you have to measure the Lx, Ly, Lz, take the average, because they will not be exactly equal, at least in there will be statistical fluctuations, and so you take the average and you know how many unit cells are there in your calculation, right. It cannot be done with one single cell like this here either, it has to be done on a system. Then you divide by that, that will give you a lattice parameter. But that lattice parameter, if you take at different steps after equilibration, will not be the same number, which means there is an error bar that you will get. Okay? You should get with that. That is the way to calculate lattice parameter at a given temperature, okay. Which also we have done. That is not the script I am showing. I am showing the simplest script to begin with. Okay. Okay? No, you will see, we will know. I mean, for example, how do I know the beginning itself whether I should give 5000 or 10,000? You can go look up the manual, it gives some standard values which are in general okay, but we will know actually how many steps it took, how many iterations and how many evaluations happened, we will know after we run, which will tell us whether this is okay or not. So, we will, when we run, we will know. No, he feels that 5000 is too small.
Yeah, but so. I mean, so if you reach the 5000, you know it was too small.
Sir, another thing is that here, sir, in the script as of now, nowhere you have given how many atoms you are giving.
No, I defined, no, 1 unit cell and I did not replicate it, just 1 unit cell.
Okay, the 1 unit cell will have, okay, so it's a BCC.
BCC, will have 2 atoms. Okay, you can run, there is no run, basically after the minimization we are just writing the data and we are exiting. when I show the script, I will also show how to actually visualize, but that is a very preliminary kind of visualization, that is not what is preferred, but more detailed one lecture on visualization we will have later. Okay. Now, after running the simulation, we should spend as much time as possible with the log file. I always tell students that there was this Nobel laureate called Barbara McClintock, I think, and she studied maize, okay. And each time you have to grow maize, right. These are genetic studies and you have to grow maize and then about 6 months harvest and then do studies. And so, in one interview she was asked whether she had chosen the wrong organism to study, because every experiment takes more than 6 months for her to do. Her answer is no, this is too fast. So, every experiment she needs more than 6 months to analyze the results. Okay. So, that is always a good aim to have. If your simulation runs for 1 day, you should probably be analyzing for 2 days. Running a simulation for 2 days and analyzing for 10 minutes is not the right approach. Okay. So, you should spend as much time with the analysis of the results as possible, and we will look at the log file also, and I will point out some things that you notice which will answer questions like this. I mean, did I choose the right parameter, did it actually do the minimization, and so on. So, before we proceed further, I think yeah, visualization is the next one. Before we proceed further, let me run this code. I have done very minimal changes to what Sushil gave me. The minimal changes are commented out now. So, there is no change from what Sushil gave me. So, this is the script, right, you have seen this. So, let me run this. Okay. You can also run serial, but I am running parallel. I am going to use 4 processors. This is the LAMPS command, which takes this input file. It says the input file, the LAMPS, this is the input file, that input file is this. Okay. You can also run just with this. LAMPS saying that I am giving you the input file is this, it will run. I think Sushil's run.sh script has this line, okay, nothing else. And you need this, because we said that for potential use this file, remember. We said fe_5.eam.fs. Okay. You can change this code if you have potential, for example, for copper or nickel or aluminum. You put that potential file in the same directory, change BCC to FCC and give a lattice parameter, and it will run for that system. Okay. That is an exercise that you can do. Where do you get the potentials? Like Ferdi said, NIST has lots of potentials. LAMPS also has the repository or repository link, so you can download and use these potentials. Okay.
I think they use the potentials not in a parameterized form as I explained, but they just
tabulated.
So if you perhaps you just open this potential file, you can show. So here you see it's this first part here is just the values for iron. And the top line says how many points and so on. So it's just on 10 points the pair potential, iron I think, and then you get the...
Yeah, it is only one iron, so nothing else, iron.
Yeah, but the first part is only the pair part, and I think then comes...
Oh, this thing part, yeah, this is a huge file. Okay, so the command is this, I run, then we go look at the log. So, it has some information. So, it says I did not give how many threads, I did not give because I did not know how to give, but probably Sushil knows. Is there? Okay. So, no, I only have a number of processors. Minus j something should be given, right? If I give, then it will use so many. I think, yeah, it is minus j2. Let me try. No. Where is it given, Sushil, at the end? Okay, I do not know. We have to look up the manual. Okay, no problem. Okay, so let us look at as you can see, the log file is basically also repeating whatever I gave as the script. Okay, the log file contains what you said, which units you used and so on. So, it is complete in itself. This is important because after a while you might have some other file you do not know for which units you ran and which values you ran. So, those of us who write programs always write immediately after reading the input data, you should write that to an output file. So, you know the simulation results are for what conditions. So, and it starts with this lattice, and you can see now there are also some extra information it is putting. Did I give this lattice spacing in x, y, z as this? So, that is added by the program. Okay. And because it is 3D and this is the lattice parameter and it is cubic, so it puts that. And it says, okay, create box, it has created an orthogonal box. And here is where I do not know your name, you are asking the question, no? I didn't, your name? Soumya. Soumya, you can see that it goes from 0, 0, 0 to 2.65, 2.65, 2.65. That is the box it creates. Okay. And this is related to MPI, right? I said some 4 processors or something. So, it is. And again I said orient. So, oriented, and this is the lattice spacing and created 2 atoms, right? Again there was a question, how many? Because there is only 1 unit cell, 2 atoms. Using lattice units, and the create atoms, how much time it took, that is also there in CPU, 0.000 seconds. In this is a small code, nothing, right? Okay. And replicate is 1, so it is replicating, and replication also finally ends with only 2 atoms. If I said 2 replication, I would have ended up with 8 atoms, you would have seen. Here it would have said we will run 1, okay. And the replicate took some time in the CPU, for doing nothing, right. In this case there was nothing. Anyway, so this is the pair style and this is the time step, this is the fix that we gave. There is a warning. Using neighbor modify every 1, delay 0, check S setting during minimization. So, I do not know why this is the warning. It does not like that neighbor modify delay when it is running into the minimization. So, warnings are okay, but sometimes it is worthwhile to try to understand why there is a warning and what it expects and so on. Okay. And neighbor list update every 1 step, delay 0 steps, check S, maximum neighbors and master list distance cutoff, ghost atom cutoff. Some of these things we have not discussed. Yep.
I think the warning is that they, for whatever reason, prefer in the minimization routine to do the
neighbor list often.
Okay.
Yeah, probably. One neighbor list and pair. I also do not know what that perpetual attributes, pair build, etc. mean. And here is another warning. Okay. So, it could lead to lost atoms. I mean, in this case we are really not running MD, there is no velocity, nothing is 0 Kelvin, does not matter. So, but it could be important, maybe if I am running a simulation, it can lead to problems with the atoms. But I think this is also related to, I mean, I am taking one unit cell and doing stuff, okay. So, it has to and asking for 4 processors to do. So, it is splitting things and stuff like that. Okay. So, it also prints these things, steps and the temperature, the energy of the pair and the total energy and pressure and volume and so on. So, all this is listed and how much CPU use is there. Here is the important stuff that we were asking questions, right. So, how many iterations it took? So, 5000 is good enough. How many evaluations it did? 10,000 is good enough for this. So, what I am saying is a priori you might not know, I mean you might have a feeling that no, 5000 is small, but you start with something, if it hits 5000 you know that it is small, if it does something like 81 then we know that it is okay. Okay. It happens here also, like I told you, this collaborator of ours, the student who was doing, he was using an energy criterion, he did not realize that the energy criterion value he was giving some 10 power minus 6 or something, here I have given 10 power minus 25, right. So, it was hitting that difference, you know, I mean very close to the minimum, maybe it is really flat and 10 power minus 6 can happen even when you are far away from the point. So, it came out, but that is there here. Stopping criterion you can see here also is energy tolerance, right. So, if you have this thing and okay, so if energy criterion is the reason why it stopped, then what is the force, right. What did it start with, what is the final force? It is 10 power minus 14. You can decide whether this force is small enough for you to stop or not, right. So, sometimes I mean in the other case where I told you about, there were some strange results and I was wondering why, and then when we opened the log file, we found that it was some 16.9 and some 15.8 and energy criterion met, it had come out. So, you have to, that is where you have to go read the log files. Okay, I gave a CG, why did it stop? Is that stopping criterion okay? How many iterations it took? Did the numbers I gave are okay or not? Everything is here. Okay. Maximum component of the force, initially it was this, finally it was this. Basically you can see there is no difference between these two norms, because probably that is the only point where things are going off. Okay. And this line search alpha and maximum move also is given. These things you will know if you know what the CG algorithm is. Okay. Energy tolerance, along with it, it also gives initial, next to last and final. So, this difference is what the energy tolerance is, but this is what it started with. Okay, it started with minus 7.6 and finally reached minus 8.2682, and between two final and just before final, that was the difference. And you can see that, you know, how many 2, 4, 6, 8, 10, 12, 14. This is also 10 power minus 14. The numbers are not different. Okay. And then there is some information about the time spent, where did the program spend its time. Okay. And then we asked it to, I do not know what these dangerous builds are, but good to know that it is 0. And it did not build any neighbor list, because we anyway did not really run. And so there are warnings here also. I think this one is related to running a small system, and this is atoms won't move. Yeah, no fixes with time integration, which is true, right. We did not give any fix, we only had a fix for minimization, we did not really run MD, and it has come out and it has written the output that we asked it to write. and you can see lattice constant has become 2.86. We started with 2.65. One thing that you can do, is this really the equilibrium lattice constant? Did it calculate it correctly? You can run once more by changing the initial value.
We give this initial value and check if it.
That is a bad move, because everything will be 0. Should give something higher than this. Okay? If you are sitting at the minimum, even if it is not, or if it evaluates forces and energies and finds that it is 0, nothing will happen.
Sir, no, so like I am saying that whatever value we have got from this run,
Right,
this 2.85 or whatever we have got,
right.
like if I give that value only as my initial configuration value.
Yes, nothing will happen. To know that 2.85 is the true minimum, I have to start from many points which are away from this point. So, let us start from 2.95 and I should get 2.855, right. I did not get 2.855, I got 3.13. There is a problem. So, let us look at, so started with 2.95, I made a mistake. Right. Now, it is getting 2.855, okay? Okay, very good. I was about to ask Sushil, but he has disappeared. No, then. Okay. So, in this case also let us look at the lamps. What did it do? Yeah, that is because I gave 2.95 one place, 2.65 another place. Yeah, so it. Twice, yeah. Now, look at the stopping criterion. I started from the other side. Okay. I told you yesterday that it is always better to stop from this side and not from the, but from a minimization point of view, you can see that if you are having a steep slope, you will get to the bottom much better than if you have a gradually changing one. And here the stopping criterion is because quadratic factors are 0. Okay, again, if you know, you have to know what it is, CG you have to go look at, but we can still see that next to last and final energy, they are pretty much 10 power minus 14, and the force criterion, they are also 10 power minus 14, and the iterations and force evaluations are much lower here, right. So, we are okay with this minimization, and we see that we are getting 2.855, and you have to do for several such points before you conclude that okay, this is the equilibrium lattice parameter for the system. Now, what I want to do is to show you two things. Let us start with this 2.65 and then come back to 2.95 if needed. First thing is, I just want to dump all images. The dump command, okay, image and every once in 100 steps or so in JPEG form, I have to dump. You can go and read the manual for the rest of the like what is type, and for image it is just type, and for movie you also have to give the size of the frame or something. Okay. So, you can do this, like I said, I mean this is a quick fix, you are running some simulation, you just want to look at, you can do, and then you will get the images, right. Even though I said once in 100, I did not run any MD simulation steps at all, but minimization by default whatever 0 it will always print, and at the end of minimization it will always print irrespective of what it is. Okay. If I make it 10 for example, because now I know that 81 is there, because remember it was supposed to go through 81 iterations. So, if I make this dump every 10 for example, then I should get several images, right. I get all these images. So, okay. Can you see it is increasing to equilibrate, right. Right. Now, you can also do a easy one, okay, instead of making these and you can just make a movie and ask it to dump, that also it will do, that is this command. And in this dump I am actually asking it to do for every step, right. What happened? Okay. 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 So, some rudimentary plotting and movies like this you can make, which is not the recommended one. We will have a much better way of visualizing data, but for this purpose this is sufficient. So, dump image, dump movie etcetera you can do, but we will have a more detailed session later for doing the proper visualization. Okay. Is there any question at this point? Are you able to run this in your computers? Are you getting the same answers? It is part of many body this thing package and that is not loaded for. So, CMake yes all is it? What is it? Make yes all. Yeah. So, there is a command make space yes dash all. Huh? So, you have to do so that all these packages are available. This is one of the reasons why I had to redo my installation twice yesterday, just installation of, did you use CMake or make? CMake, no? So, CMake also there is a command, but if you had used CMake you have to remove the header files before you restart. If you go to the LAMPS manual, on the this thing they say how to do it with several here packages with extra, include packages in build and packages with extra build options.
It's always this adios package which is missing or which
Yeah.
they used to miss.
Yeah,
And
and I couldn't fix it.
yeah, I could neither. The only solution was to
Like again,
just destroy
remove.
everything.
Yeah, I removed everything and redid with but now using that CMake make all yeah, that worked for me after 3-4 times. I mean it didn't do. I also made this mistake, CMake and then make, and that also doesn't work.
I think what happened, we tested it, cracked the data.
So maybe there this potential is not is needed. Yeah. So probably LJ will still work for you, because it doesn't work. Yeah? LJ will work. Yeah.
No, for EM potential, if many body package is there, then there is many body package only this.
But that is not there. That is what it is complaining, right? Mohan? Yeah.
Many body package is not there. That is the error message that we are
No, because that package is not compiled.
Yeah, correct. Yeah.
But Mohan did make yes all, and he thought that that includes many body. So, right? Make PS shows, yeah. But yeah, if you use the CMake, then you have to use the CMake command to, otherwise it doesn't know that it is there, and or I think there is a way to fix by giving path etc. But it's and linking these files and things like that.
LAMPS installation is easier than Govt.
Okay, good to know.
Using make and paste, it's a one line.
Yeah.
Make and paste it's a one line.
That's what yesterday 4 times I could do without problems. So.
One line, all the one line this thing is there.
Okay, so we can get it fixed after this thing.
Okay,
today make sure that you get it fixed, so tomorrow we will be able to. But in the meanwhile, yeah.
So no, in Windows you can run.
Yeah.
In Windows,
The next one that I want to show you is an example file that is already there in LAMPS, that is what I want to show. But before I do that, I had this question and I expected that Ferdy might talk about it. So, what are elastic moduli is empty because I thought that you will talk about it, and you did talk about it as the curvature of the this thing, potential curve, right. So, that is one explanation of what the elastic moduli are, but you know that the elastic moduli in a cubic crystal, how many independent constants are there? I mean, what rank of tensor it is in the first place? No, it is not rank 3. What does it connect? The elastic moduli connects what and what? Stress to strain. Strain is what rank tensor? Second rank. How about stress? Stress is? No. Why? When if you are thinking in terms of chemical engineering, think in terms of whatever your Navier-Stokes and whatever tau, right? No, it is 2. Is it a matrix or how many subscripts it has?
Okay. So like in terms of like sir, what order tensor it is?
What order tensor it is? Yeah, order. Yeah, 2. Stress is 2, strain is 2. So what can connect these two? What would be the order of that? It cannot be third rank, because if you take a third rank and if you dot one of the indices, one more index will be left, no? 4 or 0. I mean, you can multiply by a scalar. From second rank you can get second rank. Otherwise, you have to have a fourth rank tensor. If you are dotting, if you are making an inner product, 2 indices will go, because that is a second rank tensor, and you should be left with a second rank tensor. Okay. But if you have something like piezoelectric effect or something, then it is a third rank tensor, which multiplies the stress or strain to give you the other field, which is a vector. That is why it is a third rank tensor, okay, electric field or something like that. Anyway, so it is a fourth rank tensor, and in the cubic crystals, how many independent components are there for the fourth rank tensor? For isotropy, how many are there? Somebody is giving the answer, but I do not know who. 2. Okay. Why are there 2? It can be any 2, but why are there only 2? How do I know that there are only 2 for isotropic system? No, it can be shear and Poisson's ratio, it can be bulk and shear, it can be Young's modulus and bulk modulus, does not matter, 2. But how do I know that there are only 2? Why are there only 2? Where does that come from? How do I get it from symmetry? Why is the cubic one is giving 3? Yeah, so how do I get irreducible, and what is irreducible? Okay, no? Okay, so there is a series of steps. I am just going to sketch them. I am not going to do the algebra, which will tell you how to get. For example, I mean, okay, I am talking about cubic. Somebody remembers 3. Hexagonal. Now what happens? Okay. So, to understand, there is few things that is done. First is right. This is Hooke's law when it is written in all its tensorial glory. Okay, there are 2 indices here, 2 indices here, that is get summed over. I am using Einstein summation convention. So, repeated indices are summed and free indices should match on both sides, and each index which is getting repeated will appear only twice, not more than twice. Okay. So, this is now there is first one step, which is what Ferdy referred to as Voigt notation this morning, right, where you replace this by a vector, this by a vector, and hence replace this by a matrix. The way that is done in 3D is that 1 1 will go to 1, 2 2 will go to 2, 3 3 will go to 3, 1 3 will go to 4, 2 3 will go to 5, 1 2 will go to 6. Remember, this is just a mathematical trick to write this quantity in a matrix form. It also only works because both stress and strain happen to be symmetric tensors. KL can be switched, IJ can be switched, and IJ and KL can be switched. Okay. Now, in that format, now the Cij KL can be now written as, that is why I have drawn this line to distinguish, this is a 4th rank tensor and this is a matrix that I am referring to. Now, this matrix you can take, it will have what C11, C12, C13, C14, etc., C16, C21, C22, C23, etc., C26. You go C61, C62, etc., C66. Okay. Is this clear? Okay. Now, 1, 2, 3 refer to the x, y, z directions, right. So, we are writing this, when we are writing this, we are writing it in the crystal A, B, C coordinates. Those are the 1, 2, 3s. Okay. Now, if you take a cubic crystal, if I rotated it by 90 degrees and made 1 to 2 and 2 to minus 1, will you be able to distinguish? If I took a cube, I do not seem to have some cubic things here, assume that this is a cube. If I made a 90-degree rotation, will you be able to say, there is a box, more cubic than this, yeah. So, if I rotated 90 degrees, will you know that I rotated a box, the cube by 90 degrees? For cube, no, right. So, which means if 1 goes to 2, if you do a 90-degree rotation, what happens? 1 goes to 2, 2 goes to minus 1. So, let us do the transformations here. This is a trick, it works for cubic, so we will do it. There is a more strictly mathematical way of doing it, which we will not do. So, 1 goes to 2, 1 goes to 2. So, 1 1 goes to 2 2, right. 2 goes to minus 1, 2 goes to minus 1. So, minus 1 is 1 1. So, in this 1 1 and 2 2 should be the same, they cannot be different. Now, x y or y z or x z does not matter, right, cube, they are all the same. Instead of doing this rotation, I could have done this rotation about this. I can say 1 goes to 3 and 3 goes to minus 1. So, 1 1, 2 2, 3 3, all 3 should be the same for cubic. Do you agree? There are 2 levels of transformation, 1 1 went to 1. So, this 2 2 went to 2, that is why in this 2 it is coming. Please remember that. Okay. Now, consider something like, okay, this rotation 1 2, I do not know which one it makes 0. I think this one let us take. Now 1 went to 2, 2 went to 1, minus 1. So 1 2 should be minus 2 1. Okay. So 6 should go to minus 6. So 1 6 should go to minus 6 1, right, in this, because this is only for 2 indices, we have to translate it. And similarly you can do other operations to show that there is some other condition which shows that C16 should be equal to C61, and a number cannot be minus of itself and equal, so it should be 0. So this is how, I mean somebody said symmetry or something, right? Yeah. This is how you use the symmetry arguments to show that how many non-zero components are there and how many independent components are there. By the way, when 3 independent components, how many non-zero components?
Well, for this case, for this,
For cubic.
okay, for cubic,
C11, C22, C33 should be equal. So which means they are not independent. So there are at least 3 non-zeros here itself. Okay. Now in cubic 1 2 1 3 2 3 are also the same, and 1 2 2 1 are the same. So this entire 3 by 3 are populated, but each one of these 1 1 2 2 is 2 2 1 1, right. So and similarly if you go to this 1 2 1 2, 1 3 1 3 2 3 2 3, they are the same. So that is why 3 independent components, C11, C12, C44 or C66, that is. But look at C44, which is what, C2323. There are 4 of them, because 2 3 you can flip, the other 2 3 you can flip, and both of them you can flip, and so on. So the number of non-zero components is much higher than number of independent components. Independent components there are only 3 for a cubic one, and you can also think of this, I mean that is also sometimes an answer. Why are there 3 for cubic? The anisotropy can be represented, cubic anisotropy represented by one number which is called Zener anisotropy parameter. So there is a relationship between the 3 for isotropy. So one relation, so one independent component goes away, there are only 2 left with for isotropy. Those 2 can be any 2 moduli. Okay. These are the components of the tensor. There are combinations of this or averages of this which give you the what we typically measure in the lab, like Young's modulus, shear modulus, Poisson's ratio, and so on. So you can get them. Okay. And in terms of these numbers you can also write those, for example 2 C44 by C11 minus C12, is it anisotropy ratio?
C11 minus C12
By 2 C44
is equal to C44.
C44, yeah. So that is the Zener anisotropy parameter, for example, which tells if it is greater than 1 0 0 directions, or if it is less than 1 1 1 1 directions will be softer in a cubic system, and so on. Okay.
It's interesting.
Okay.
I mean, if you have an anisotropic system, and most single crystals are anisotropic, yeah. For example, iron has a different elastic modulus in the 1 1 1 direction as it has in the 1 0 0 direction. I think it's softer in the 1 0 0 direction. Yeah? And I think the most isotropic among the elements is tungsten. And the second most, I think, is aluminum.
Aluminum, yeah.
It's pretty isotropic, but that's by chance. Yeah? And of course, a polycrystal normally is considered as isotropic because you have all the orientations, so the different elastic moduli somehow average out.
Okay. Now, when we say let us use lamps to calculate moduli, what is it that we are calculating? It is not Leonard-Jones. I cannot go take the curvature at the minima point, right. Okay. So, there is the script that is written which uses this idea. So, let us look at the script and let us see if you identify what is being done in this script. This is a model script that is given by in LAMS itself. So, this is where this Voigt deformation component 1, 2, 3, 4, 5, 6 is given. When they say 1, what they mean is in the strain or stress it is 1, 1. So, 4, 5, 6 basically are the shear, 1, 2, 3 are the dilatation or the diagonal components. Okay. So, include init mod. Let us look at what init mod is. Okay, only uncommented one is units metal, variable some CFAC is 1 point e power minus 4, variable C units is some string called GPA. Okay. And E tolerance, F tolerance, maximum iterations, maximum evaluations, all that is there. Boundary is periodic, null dimensions, and it is a diamond lattice. Okay. I do not know how many of you know the diamond lattice. Do you know what diamond lattice is? You do not know what diamond lattice is? Diamond lattice is also a cubic lattice. Yeah. Yeah, silicon. I mean, we are calculating this for silicon. I mean, this code is for silicon, that is why it is. So, it is also a cubic lattice. I think the way to understand it is to think of an FCC and then 2 of the interstitials, right? One on this side, one on the other side.
Okay,
in the unit cell, right. You put, so carbon, silicon, etc., they get to this crystal, germanium also probably. So, you can do, I mean, you can go back, change the code that I gave for BCC and you can plot the unit cell and you will open it and see, you will see where the atoms are, right. One unit cell you can put, you can use the LAMS to learn your crystallography also. Okay. So, it will put the diamond and with the given lattice parameter A and variable A is equal 5.43. Remember, units are metal. So, this is 5.43 angstroms, that is what they are generating it with, and the region you know, how to create box you know, create atoms you know, mass is also given. And if I had written this code when I changed some 9.5, I would not have had trouble. In one place only I would have changed. Okay, anyway, so this is a good programming practice. I mean, define variables and so this part is clear, init.mod. I am also showing this script because like in every programming language, you can have function calls, right. This is a script and it is having several scripts which are included into it, that is all. I mean, instead of, you could have written all this in the same program itself and also could have run it, but you are separating it out and make it neater, cleaner, so on. Okay. So, what is the next one? Include potential.mod. What is the potential module? Pair style is SW. Do you know what SW is? Stillinger-Weber. Okay. I do not know how many of the others know. That is a very common potential used for silicon. Okay. And pair coefficients again you can see star star SI.SW, that is what, and I had some FE, EAM, etc. So, that potential file is also here by the way, and you see that EAM potential file and you see this potential file.
This is a case which is not tabulated, but is a function. And I think the Stillinger-Weber potential, they use some angular dependence necessary for semiconductors, because semiconductors have the covalent bond, and this covalent bond is strongly directional dependent in contrast to metal itself.
Yep.
So I went through the other EM potential as well. So once can you, like, you probably time won't permit, but once can you go through the potential file?
Yeah, we will go through. In fact, you can write in some papers, they will just give the parameters. If you know the parameters, you can write the potential file yourself or write a small C program which will do that and give you the potential, and it can be written using the C program in the format in which LAMS will accept. So, if you read a paper, you can take the parameters, you can generate the potential and give it. So, we will take a look at it. I think there are also programs which do this, and their manuals explain what it is, but LAMP's manual also explains what the expectation it has from the EAM potential. I do not think, I mean whether you give one spacing or tab, I do not think matters for these potentials as far as I remember. These are not like formatted that the tab spacing for example will affect. I do not know how it is in GROMACS, I think here it does not matter.
It's a
Lens I have tried, so if you are providing pan coefficient, then spacings matters.
It matters?
Yeah.
Okay. I do not know, we can take a look at. So, it is possible to write. Ferdy, I think you, Rolf's code had, I do not remember spacing being, okay, anyway, we will take a look at. So.
Sir, no, so I want to ask that all those specifications are given in this force field file or potential file only, or what? So
Which ones?
So like my bond coefficients and whatever I have.
Yeah. So, you can see they have written epsilon sigma a lambda gamma cos theta a b p q tolerance, that is all is here. And that paper describes original Stillinger Weber from 1985, why these are the parameters and what is the form where you will plug these numbers in.
Sir, and what about the units in these files?
Metal, no?
Okay.
We defined metal, right?
Yeah, it is given.
Yeah, metal. We started with metal, no? The other file, so it is metal. Okay, so that is also a simple file, and let us go to the potential mod. So, pair style and neighbor modify, check S is there, and minimization style is CG, and minimization modify also is given. I mean, what is the maximum line? $D max might be there in the there is a place where he is defining minimization parameters. So, let us take a look at where it is. Hmm? Oh yeah, D max. Okay.
Sir, Dmax it is able to take because I have already included init.mod first and then I am
Then
including-
yeah,
Okay, so that sequence also matters.
will matter. Yeah. If otherwise it will complain that it does not know what this D max is or give an error message, you can. Okay. So we are at what? Potential we have seen. Potential we have seen, init.mod we have seen, and there is a fix. Why is it uniso? Box relax.
Sir, my system is now the structure that I have defined with the
It is still cubic, it is diamond cubic. So,
Okay, sir, because I am finding the elastic moduli now. So, so in that case, the deformation might not be similar in all directions.
yes. So, it is going to destroy when I pull in one direction, I do not. So, this is also, I mean, even though I said okay cubic, iso, etc., there are two things. One is uniso includes iso also as a special case, just they happen to be equal, and you expect in the simulation they will turn out to be so, but in some cases they do not, that also we have seen. Okay. In this case certainly you cannot use, because I do not know what this fix is. Equilibration maybe you can still use the iso, because it is cubic it will equilibrate, but the moment you start pulling along one direction or two direction or giving shear and so on, then you cannot expect the deformation to be isotropic. Okay. Okay, so there are whole bunch of variables that are defined. So let us take a look at this uxx perturbation, right, that is what he calls variable direction is 1 and displace mod. What is there in displace mod? So, what did he do? What is being done? Okay. So, basically to get the modulus, we are still going to get the region near the minima, and we are going to map out the energies by making small deviations from that position, minimum position, and we are going to fit that data to a parabola, and the curvature is going to give me the modulus. The way you, or the other way to think about is that how much is the elastic energy if I give some strain? Half k is C11 in this case, or 1,2 depending on what you are giving, and the epsilon is whatever you are giving as the strain, square of that, right, delta. So, half C11 delta squared will basically give me the energy, which I can evaluate from MD, right. I give this displacement, I calculate the energy. So, left hand side is known, displacement is known, I can calculate the corresponding moduli. But because it is cubic, for example, C11, C22, C33, I will do all three of them, I will take an average and I will report that as the C11, which is equal to C22, which is equal to C33. That is what is being done. That is why there is displacement, there is minimization, and get the energy. And you can have this displacement both as positive and negative. So, you about the minimum position, you can go here, you can go here, you know these values basically, and you can make many more evaluations, and you know that so I can calculate this, I know this is what I impose, this is the energy I got, that will give me an value of C11. So, that is basically this code. So, you do displacement in 1, displacement in 2 and 3, 4, 5, 6, you do and you calculate, right. That is what prints out. Okay. Why are these factors of 0.5 for this 1, 4, etc.? C12 and C21 are supposed to be the same, but in your simulation you will get the values, but you will take the average. Without loss of generality, it is the same, there is no difference. Even if they are not the same, there is no way for you to separate it out. Okay. So, the point I am trying to make is some of you who have done probably elasticity, right, from mechanical engineering, probably you see all this, you know. But if you are not, and if you are doing, probably you also need some background into it. There is this nice book called NI, Physical Properties of Crystals and Their Representation Using Matrices and Tensors. Okay. So, there you will see all this symmetry and everything explained. It starts from very simple things, and within 4 or 5 chapters reaches 4th rank tensor, and probably one of the best that I have seen. All that background is needed for you to understand exactly what it is doing. So, one aspect that we have been emphasizing, that you need to know a little bit of StatMech to really understand what MD is doing, and on top of it you also need the material science if you want to use it for the material science purposes. Okay. I am not spending too much time because this is an example that is given, it is not our example, but I will show you that I can run. I don't know, I think we have gone much beyond our, okay, that is it, done. Okay. So, please do take a look at the code. I know that from the lattice parameter code, which was some 15-20 lines, to this is a big jump, but this is much better written code. Variables are separated, there are different like function calls, they are included. and methodically it is done, and it also involves a little bit of background that you need to know to do this. We have, I mean, based on this, one of our students, Kamalakshi, has written a code and we have evaluated elastic moduli. But I mean, it is no different from this. We just took and modified the potential, or we gave for an alloy potential to evaluate moduli for an alloy and so on. Other than that, we did not do much of a change. So yeah, so that's a tricky problem. So if you have higher temperature, you anyway have some movement. Okay. So getting good statistics, getting good numbers. So most of the times you will see that these are done for 0 Kelvin and matched with either first principles calculation or some other measure you have for because first principle calculations people also do some strange thing. They will build in such a way that at 0 Kelvin it will give you the room temperature moduli. Okay. So sometimes that is also strange, but anyway, sometimes these potentials use those values and match. In those cases, if you use the potential in your MD simulation, you should get the same moduli. Once you do that, you know that your script is okay. That is just a sanity check. Then you can take another potential where you want to evaluate moduli for which you do not know the moduli. We did it for copper with some aluminum. We have mixed potential. Energy method also. Yeah. The 0 of the, I mean, yeah, take the minimum of that curve, yeah, fitting it. Maybe that script also we can share at some point. Yes. Yeah. Okay, so I had originally planned to do one more thing. I think by now we are all saturated. That is also a much more complicated script, because we have iron crystal in contact with its melt, and we are trying to evaluate the melting point. I will just show you the idea. We will go through the script tomorrow. The idea is as follows. It is again an interesting thing. So this is what we generate. So this is BCC iron and this is the molten iron on either side. To be consistent with periodic boundary condition, there are two interfaces, solid melt interface. Okay. Now you can approximately get the melting point. You can think, right, I take this full as the melt, start cooling down, at some point it has to become a crystal. You can measure that temperature, and then from the crystal again you can start increasing the temperature, you will get the entire thing molten. So you know that temperature. Strictly speaking, those two should be the same. Do you get it either in experiments or in MD? Why? Yeah, but I mean, we might not freeze in the amorphous structure. I mean, it can get to the, in fact, it does get to the structure, but there is still some hysteresis. Think in terms of experiments. Why is there in experiments also, and obviously iron is not freezing into a amorphous state there, right? So why does that happen? Do you know? This is a material science question. I mean, it is unfair to ask the chemical engineers, but yeah. So. Okay. In general, it is always easier to take a molten system and keep it as a molten system below the freezing temperature than to take a solid and heat it above the melting temperature and keep it as a solid. The simplest way you can understand is that when the solid is getting molten into a liquid, the bonds are breaking, but the solid already has broken bonds at the surface. So melting will always start at the surface. So melting does not need nucleation, that is what probably you meant by ordered structure that has to form. So there is a nucleation barrier in the other way. So, there is always a hysteresis, but this is sufficient for us to know in which range the melting temperature lies, right. Once you know that, yesterday Ferdi drew that curve, right, solid, liquid, the free energies. So, one point where the solid and liquid free energies are the same is the melting temperature, that is the thermodynamic definition. Now, if I take such a system coexisting and keep it below melting temperature, what should happen? This will grow, because you are below melting temperature, it will try to eat up some of the liquid and reach its equilibration, which means the potential energy and kinetic energy in the system will change. On the other hand, if you keep it just above the melting temperature, the liquid will grow, again will lead to potential energy change. So, you track the potential energy change by keeping it quite close to the melting temperature, find that system for which the potential energy curve, for example, is flat, there is no change, which means there is no melting or freezing that has happened. So, you fit it and you get the melting temperature. So, this is how we do this. This is called the coexistence method, and one of our friends, Mohan knows. So, Ramakrishnan and Shankara Subramanian and Fani Kumar, they have a paper where they explain this in great detail, and that is what we used finally when we implemented also, okay, to get this. So, this script is what I am going to share with you. So, some of you might want to do, you might want to study the properties of the solid and melt, right. What are the properties of this? So, for that then you need to exactly know the melting temperature, you have to keep it there, otherwise things are not going to happen, right. So, how to evaluate that is a script that we will look at tomorrow, and I will show you. Yeah.
For doing this, you probably had to run many simulations at different temperatures.
Yeah. First you start, take a solid, start heating it up, note down where it melts, and then cooling down, note down where it solidifies. So, you know the range. Once you are in the range, then you only need to run several simulations by taking the system temperature. Of course, I mean it still involves lots of stuff. See, with the temperature the lattice parameters are different. So, equilibrium you have to get, otherwise those energies will also change. So, to keep a stable solid melt interface and a large enough system that small movements here and there does not completely freeze or completely melt, you have to do a little bit of trial and error, but otherwise you know. This is equilibrated to, you can see,
So like
this is the MD step,
number of MD steps is given, okay, so probably it is 150.
and it is 0.001 metal. So, that much time you have to equilibrate before you can take. Okay, any other question or clarification? If not, we will stop.